This video is the second part to the mean value theorem for integrals and the second fundamental theorem of calculus. So if we start with this example, use the fundamental theorem of calculus to find the integral from 1 to x of the t squared minus 4t plus 1 dt. While the fundamental theorem of calculus told us simply integrate and substitute in your upper and your lower limits. So if we do that, we end up with, using power rule, t cubed over 3 minus 4t squared over 2 plus t, and we're going to evaluate it from 1 to x, which would then give us x cubed over 3 minus, I can simplify this to be 2t squared or 2x squared plus x minus 1/3 minus 2 plus 1. And we can simplify all of this to equal x cubed over 3 minus 2x squared plus x. And this would simplify to positive 2 over 3. Next part is telling us take the derivative of our answer. Well, if you recall derivative power rule, you would bring down your exponent, subtract 1 from that exponent, and that was it. So minus 4x plus 1. Derivative of a constant is just 0. So this is our derivative, which if we simplify it, becomes x squared minus 4x plus 1. So now it's asking us, what is the basic result? Well, the basic result is that the derivative of what we had integrated is essentially the same thing we had to integrate. The only difference is now that it's in terms of x rather than in terms of t. And this is because when we took the derivative of our integral answer, the derivative of a constant is just 0. So what does all of this have to do? Well, that brings in the second fundamental theorem of calculus, which states that if a function is continuous on an open interval, then for every x in the interval, if you take the derivative of an integral from a constant to a variable, then that's essentially the function inside with the variable changed. And it says the same exact thing here, changing the variables. A is still a constant and u is now a different variable. So this is what it says here. Now let's explain all of this. Say you're taking the derivative of a definite integral whose lower bound is a constant and whose upper bound contains a variable. What this is saying is that the constant on the bottom doesn't matter when we take the derivative of the integral, because the derivative of the integral is the original integrand, but with the variable changed. And all you need to do is learn this pattern. So let's do another example. For f of x, that's equal to the integral from 2 to x of 1 over 3t squared dt, they're asking us to find f of x first. Well, there's no derivatives of integrals here, so simply we're going to integrate it. That would bring us to, we pull out the constant, which is 1/3, and then we bring up our t squared to be negative. So we'll have 1/3 integral from 2 to x of t to the negative 2 dt. When we integrate that, that gives us t to the minus 1 over negative 1, still multiplied by the 1/3, and we're going to evaluate that from 2 to x. And that would give us negative 1/3 x minus a negative 1/6. So that gives us negative 1/3 x plus 1/6. And this right here is our f of x, capital F of x. Well, for part B, we can use our f of x and replace our x with 2. So we have negative 1/3 times 2 plus 1/6, which is then negative 1/6 plus 1/6, and that's 0. Now they want the derivative. Well, here's our function. If we take the derivative of this here, we end up with, using power rule for derivatives, you would bring it up. So that would give you negative 3x to the negative 1. Taking the derivative, you bring down your exponent and then subtract 1. So it would give you this. Did I do this right? Hold on just a second. If I pull out the constant first and then take the derivative of this, that'll give me negative 1/3 negative 1x to negative squared, which then gives me 1/3 x squared. This is your derivative. Well, now it wants you to use your derivative and substitute in 2. So 1/3, 2 squared gives you 1/12. If you look at example 5, though, you have take the derivative of the integral of this function. But if we recall that the second fundamental theorem of calculus says that if you're going to take the derivative of an integral with a constant and a variable as your limits, then that's equal to the integrand with just the variable changed. Well, that's what we have here, taking the derivative of an integral with a constant to a variable of some function. Well, that's using second FTC. Then this would be just the square root of 1 plus x squared. Wouldn't have to integrate it, wouldn't have to take derivatives. That's simply what it would be. Well, now they want us to take, this is a whole different example, find the derivative of our function given that our function is this. Well, we have to use the first fundamental theorem of calculus, which gives us sine of t, and we're going to evaluate it from negative pi thirds to x cubed, which is then sine of x cubed minus sine of negative pi thirds. So we have sine of x cubed plus square root of 3/2. And now they want us to take, this is our f of x, capital F of x. They want us to take the derivative. Well, we know that our square root of 3/2 is going to cancel, but here you've got chain rule. Favorite type of derivative to take. Our outside function is sine. Our inside function is x cubed. So you take the derivative of both. Derivative of sine is cosine. Derivative of x cubed is 3x squared. So substituting it all back in, it's the derivative of the outside with the inner function staying the same times the derivative of the inside, which was 3x squared. And that is it for second fundamental theorem of calculus. Notes.